In this video, I'm going to go over 6 regression basics. So these are things that you really should know about regression analysis, and I'm guessing they're probably not in your other textbook. Okay, and so those regression basics are first that there are different objectives of regression analysis, and what that objective is actually should dictate, well, what should you hold constant. Second, when you have some estimates from a regression, what you are seeing is the average effect or the average association, how those variables tend to move together on average. Third, what do insignificant estimates tell you? 4, p-values are not what you think they are. 5, hypothesis tests. I'm sort of going to tell you not to do them, but don't tell anyone I'm going to tell you not to do them. And 6, why are we here? Is our goal in regression analysis statistical significance, or is it something else? Okay, so there are 4 main objectives of regression analysis, and the first one is what we're probably most familiar with, of estimating causal effects. We want to know how some factor affects some outcome. So the classic one is how a college degree affects income, or maybe how much does a college degree affect the probability that someone gets into a car accident. Okay, next, regressions are often used to forecast or predict some outcomes. So you may want to know, what is the best guess for the value of an outcome? What's the predicted likelihood of some event occurring? So in contrast to what's above here, you may want to ask, well, what's the probability that someone will get in a car accident in a given year? And maybe whether someone has a college degree could actually help towards predicting that outcome. And so your objective isn't to find the causal effect of the college degree, but rather use that to try to help you get a better forecast of the likelihood that someone gets in an accident. And that is what an insurance company trying to set prices for different types of people would be more interested in. All right, third, you may want to determine the predictors, the different predictors for an outcome, or what's the best predictor. And so a study that came out a few months ago found that people who drive an expensive car are more likely to be a jerk. So driving an expensive car probably doesn't cause someone to be a jerk, but it's indicative of being a jerk. And by the way, they measure jerk as whether they stop for pedestrians. Okay, is swearing a sign of intelligence? Well, again, swearing doesn't cause intelligence, rather it may just be a sign of intelligence. I believe some studies found that as well. Okay, and then fourth, you may want to analyze relative performance. And so if I were to tell you that there are 2 military recruiters, A and B, and recruiter A signed 18 high-quality contracts in a given year, recruiter B signed 14, then I asked you who performed better. Well, just based on this, you can't really answer that, because it could be that recruiter A is just sitting on his butt in some Dallas recruiting station where people are always walking into the office, whereas recruiter B perhaps is recruiting in, say, rural Vermont, and it's not so easy. No one's walking into the station. You actually really have to go out there and canvas and try to recruit people. And so recruiter B getting 14 recruits might actually have done better than recruiter A getting even more at 18. Okay, when you do this, then you really need to make sure that you condition on the right set of variables. That's a separate lesson. Okay, so what objective you have should dictate what should be controlled for. And so the easy ones to do are forecasting, where typically you want to control for almost everything. You might have to be aware of a couple things such as reverse causality, but for the most part, you throw the kitchen sink of variables into the model. For determining predictors of an outcome, my recommendation is that you use one explanatory variable at a time. You don't have control variables. Maybe there's a categorization of variables you want to use, such as different racial ethnic groups. But it's basically one concept at a time. And so, for example, I'm interested in whether that expensive car coming towards me is being driven by a jerk, meaning he may not stop for me. I'm not interested in whether that car is indicative of that guy being a jerk, conditional on whether he talks back to his mother or whether he talks with his mouth full or something. Okay, what isn't so easy is knowing what to control for when you're estimating causal effects or analyzing relative performance. Then you have to be much more careful about what you need to control for. Okay, next, let's think of this conundrum. Let's say that somehow you capture that the true causal effect of a year of schooling on income is $8,000. And then someone sees that and they say, hey, I received a PhD in economics. That means I was in school for 21 years beyond kindergarten. And I'm earning $25,000 a year waiting tables. So the effect of a year of schooling can't be that high, can't be $8,000. Okay, so how would you respond to that person? Well, what I would say is regression estimates are average effects or associations. It's not an effect that gets attributed to every single person. And so a good example of this is parental divorce, how parental divorce affects children's academic achievement. And so you might have a model like this: score equals a bunch of x variables, and then you have beta 2 times divorce. And here's the thing, supposing, of course, you can actually effectively isolate the causal effects. So some would be negatively affected by the divorce, meaning their beta 2 would be less than 0. That is, some kids might be positively affected by the divorce. It might get them out of perhaps a bad family situation. And so their beta 2 would be greater than 0. And then some kids just would totally brush it off. It wouldn't affect them, or they're so smart in school that it doesn't matter if their parents get divorced or not. And for those kids, their beta 2 equals 0. And so what we estimate is the average of all these different betas, the negative ones, the positive ones, and the ones which are equal or at least very close to 0. That's what we're getting for the average divorce. And this will have implications in a moment. Okay, number 3, what does an insignificant estimate tell you? Okay, so you get some estimate perhaps on your key x variable. It's 0 or close to 0, and it's insignificant. What can you learn from that? Well, there are 4 possible explanations. And the first one is that, well, indeed, there is no association or no effect of the key x variable on that outcome. Okay, second, there is an association, but you're not able to detect it because there's some bias or perhaps some bad modeling, and that's counteracting the effect. So you're not able to detect the true effect. Okay, third, there is an association or there is an effect, but there's just not enough power. There's not the observations, there's not the variation in the key x variable to allow you to detect it. And then fourth, there could be varying effects in the population that counteract each other. So let's go back to that divorce example. It could be divorce has a real positive effect on some children, and it has a real negative effect on other children, and those effects are just counteracting each other. And so it doesn't mean that the divorce doesn't affect these kids. It just means on average, we're not able to see any evidence that the divorce is having an effect on kids. Okay, so when you have an insignificant estimate, the incorrect interpretation that's commonly used among all these PhD academics is that there is no effect. But the proper interpretation is that, well, there's just no evidence for an effect or no evidence for any empirical relationship. Okay, so a great example of these incorrect interpretations saying there is no effect occurred with the research on the hot hand in basketball. And so hot hand is like being in the zone. It can happen in sports beyond basketball. It can happen even in dance. So the hot hand is basically being at some elevated level of play, where in basketball, you're more likely to hit any shot that you take compared to your normal state. Okay, well, for 25 years, from 1985 to 2009, all research on the topic found no evidence for the hot hand in research. Okay, so no hot hand was detected. And what their conclusion was that the hot hand is a figment of our imagination. The hot hand is a myth. It doesn't exist. And when all of us fans and all of us players argue about the existence of the hot hand, we're just making some natural cognitive bias of seeing patterns in data that's actually random. It turns out that there are other explanations for their insignificant coefficient estimate and their inability to detect the hot hand. And so if you recall from the last slide, there were 4 explanations for an insignificant estimate. So the first one was there is no association, and that's what these people concluded without considering the other 3 possibilities. And it turns out that the ones at play were numbers 2 and 3. Okay, so number 2 said there is an association, but there is some bias affecting the estimates that's making you unable to detect the effect. And that's what was at play there, that there was a problem with bias from measurement error. And so you can read about that later in the book, or we'll have that in a later video as well. There's also the problem from number 3 from the prior slide, that there just was not enough power, not enough observations in the prior data, that they had at most 2,000 observations. And so there were these other explanations for why they had an insignificant estimate. Okay, and so the conclusions from these researchers and from the Nobel Prize winners who were discussing it should not have been the hot hand is a figment of our imagination, or there is no effect. What they should have said is there is no evidence of the hot hand. We are unable to detect the hot hand, not that it's a myth. And it turns out the hot hand is real and it's out there. That's what the new evidence shows. Are there implications for the search for aliens? Well, you can read about this in my book. But basically, some people argue that, hey, we haven't found evidence for aliens yet, and thus that's pretty good evidence that we're alone in the universe. In fact, there was a Wall Street Journal article on this. And that's the same poor logic, that what the conclusion should be is that there is no evidence for aliens out there, not that there are no aliens. And in fact, just as with the hot hand in basketball, our tests for whether there are aliens out there are really poor, weak tests. Okay, the picture that was on the front was a picture that I took, and I took a couple other kind of cool pictures here. Okay, and so you can tell that these are basically, these are waves, and what I was trying to capture were maybe an image of Justin Bieber or Kanye West, something that I could perhaps sell on eBay. And if I had continued to take more and more, perhaps millions of these pictures to try to see patterns or shapes in these different pictures, then eventually I probably would have seen a celebrity figure in the pictures here. Okay, well, that same logic went into this right here. This is a correlation done by Tyler Vigen, where he correlated the number of people who drowned by falling into a pool in a given year with the number of films that Nicolas Cage appeared in. And look at that, it's a pretty good correlation. So he found a correlation of 0.67. He found a p-value for that correlation of 0.012. So most people would say, hey, look, there's a 98.8% chance that Nicolas Cage movies are correlated with people drowning in the pool. But his movies are not that bad. There's a couple good ones. Moonstruck is a great movie. And so what this guy probably did here is that he took all, I'm guessing, hundreds or thousands of actors or actresses and many different outcomes like falling into a pool and other things, and he tried to find one that had a nice, cool correlation that was statistically significant. Okay, so what this says is that p-values are not what you think they are. And so if you have a p-value of 0.05, it does not mean that there's 95% certainty that the empirical relationship is real. What needs to be considered are a priori, meaning before the fact, chances or probabilities that there could be a relationship in the first place. Now the problem is this is a very subjective measure. What's the a priori probability that there could be a relationship? And so that basically takes away the objectiveness of statistical testing. What Regina Nuzzo found in an article in Nature back in 2014, and the medical researcher from Stanford, John Ioannidis, found something similar. And basically what Nuzzo said is that if there's a 50-50 chance over whether this empirical relationship is real, then if we have a p-value of 0.01, that translates into only an 89% chance that there's a real relationship. Okay, 0.05 p-value means only a 71% chance. And if something is a long shot, let's say only 5% chance there's a relationship, then 0.01 p-value means only a 30% chance there's a relationship. Okay, so these prior a priori probabilities really need to be taken into account. Okay, so what does this say about hydroxychloroquine, which some have said might actually help improve outcomes? Well, let's think about this. Let's say that there are 1,000 ineffective drugs or treatments that are being tested. You can even do it in a randomized controlled trial for trying to reduce the mortality among COVID patients. So how many would those show that they actually reduce mortality? Let's say at the 5% significance level. Okay, well, think about a two-tailed test, and 2.5% would show a significance on the positive side, 2.5% on the negative side. So roughly 25 of those 1,000 ineffective drugs and treatments would show that they actually improve outcomes. And what this means is that if there's anything that's found to be significant, it should be retested. All right, number 5, hypothesis test. Don't do them. Okay, now let me qualify this. This is my recommendation. There are many people who feel differently, so take it with a grain of salt, but I'll tell you why I feel this way. So basically what I'm saying is, don't use these terms. You reject the null hypothesis, you accept the null hypothesis, and you do not reject the null. And this is why. Okay, first, accept is wrong, as we just discussed. Okay, basically, you rather should say do not reject. You can't reject, there's no evidence. Okay, that said, reject and do not reject, in my view, are just way too absolute. Okay, especially given the fact that they are often wrong. We get these type 1 and type 2 errors. Okay, also, as we just learned also, there is ambiguity in p-values, and there's ambiguity in insignificance. We don't know what it means because there are so many possibilities. Okay, perhaps more importantly than all this is that hypothesis tests do not account for the validity of the study. Okay, how valid is it? Are there alternative explanations that have not been able to been ruled out? Okay, so I don't like any decision on the null versus the alternative hypothesis. What might be okay then is just saying, okay, it's statistically significant at a given percent level. That seems fine. Okay, so how do we characterize results instead of using hypothesis test? Well, first you want to consider that before the fact probability. What's the probability there could be an effect at all? Okay. You want to describe the strength of the evidence. This is probably the best thing you can do. So say, here's what I find. I consider it weak evidence. I consider it maybe strong evidence, overwhelming evidence, if in fact the results are very strong and you've been able to rule out all the alternative explanations. Okay, so describe how strong the evidence is. 0.01 should be the benchmark, but still, even on long shots, then you want to say, hey, this isn't necessarily that strong evidence if you do get something at 0.01. Anything above 0.01, well, it's hard to say that it's strong evidence. Maybe supports theory. But, that said, if you get 0.011, that is pretty much the same as 0.01. That's just a little statistical anomaly for the difference. Focus on something being practically significant, meaning an estimate that's meaningful. It's a meaningful impact, not just some little trivial impact. So focus on that as well as the statistical significance. And of course, consider validity. Okay, again, are there any alternative explanations that just have not been addressed? Okay, so why are we really here? Why do we do research? Why are you learning about research? Well, research serves a purpose to try to inform society so we can make better decisions. This can be for individuals where they make better decisions on health behaviors or how to best raise their children, or it could be more for society where we want to be informed as we determine public policy that might be optimal for us to do well as a society. Okay, and so what do we want to see in other people's research? Basically, do we want to see their attempts to achieve statistical significance? Or do we want to see their efforts to get the best, most accurate answer possible? Okay, and so that raises the question, is statistical significance your goal in research? And the answer is no. Your goal should be to develop the best model that gets you the most accurate, unbiased answer. Okay, now I know everybody wants to have an impactful thesis or just have the satisfaction of finding statistical significance, but unfortunately sometimes it doesn't happen. And that's okay. An insignificant finding is okay. And so this brings up the topic of p-hacking. And what p-hacking means is that people are manipulating the model or changing the model until they get a good p-value, until they perhaps get a p-value that just comes under a threshold, one of those key thresholds of 0.05 or 0.01. And so this is not so secret number 578, that yes, researchers, academics, people who are doing consulting, that sometimes they manipulate models to get something interesting. It happens, unfortunately. Okay, and so the best practices are first, ideally you would develop the ideal model or the optimal model before you estimate the model. Okay, next, don't try to find statistical significance. That is not your goal. Don't try to convince the readers that your conclusions are correct. Yes, you can present your results, give your conclusions from that, but you want to be honest and forthright about what those potential pitfalls are that maybe you weren't able to address, and whether you can answer a research question with any amount of certainty. Be honest and forthright about things. That way we're all better off. Okay, so I'll end with this Yogi Berra quote, where he says, "If you ask me a question I don't know, I won't answer."